My name's Dave Farley. I'm a newly independent consultant and software developer. This talk today is a new talk. I want to give everybody fair warning that it's actually a significantly more technical talk than my common conference talks of late. So if anybody's afraid of design concepts and code, now's the time to go and leave and find something else, because that's what this one's about, really. I wanted to talk about acceptance testing for continuous delivery. This is a topic that's close to my heart. This is one of the things that one of my contributions to the book, amongst others. And I think this is really important. And often continuous delivery gets kind of, we think a lot about the automation of deployment and the configuration management, and all those things are important. There are lots of things that are important in making continuous delivery work, but the automation of testing is crucial, in my opinion. And I want to talk about some ways of approaching that make it easier to live with, because it's hard to do this stuff well. I want to talk a little bit, so what's the role of acceptance testing? If you've seen in my presentations before, this is my picture of a deployment pipeline, and really what we're talking about is a series of validations that any change will go through to find out whether there's something that's broken. So we're going to have a multiple levels of validation as we go through the process. I would probably say that these bits are what I would count as acceptance testing. So I'll talk more about what I mean by the definition of that. The bit that I'm going to focus on today, though, is largely this bit, which is acceptance testing in the purest sense. And what I mean by that is that it's the automation of tests around asserting that the acceptance criteria for your stories are met. So I think of this as kind of the automated definition of done, an executable specification of the behavior of the system, that kind of stuff. So what's an acceptance test? So it asserts that the code does what the users want of the system. A unit test asserts that the code does what the developers think it ought to do. An acceptance test is different to that. It's focused on the behavior of the system from a user of it. It's an automated definition of done. It asserts that the code works in a production-like test environment. So you're not just testing the behavior of the system, you're testing it in a production-like simulation, a simulation of the production environment. So you're asserting kind of more broadly that the software is deployable, is configured correctly, and all of those other things, as well as just the interactions with the system. It provides feedback on stories and kind of closes that feedback loop. Often it gets talked in these contexts: acceptance test-driven development, BDD, specification by example, executable specifications, those sorts of ideas. So as I said, I think the shortest form of the definition from my perspective is an acceptance test is an executable specification of the behavior of the system. And if you think of it that way, it's a valuable way in to the approach. So where does that sit? So this is, again, a slide that's kind of pinched from other presentations. I think of software development as a series of interlocking feedback loops, and the establishment of these feedback loops is crucial to making it work effectively. And the feedback loop that I'm talking about today is really this. It's not the kind of inner TDD cycle. That's covered. That's fairly well covered. But this one, I think, is often less well covered. The outer loop is kind of the feedback loop from idea to getting valuable software in the hands of a user. It's a really important feedback loop, probably the most important one, but I'm just talking about this one today. So what's so hard? Why is this difficult? Why do people struggle with doing these sorts of tests? So part of the problem is that tests break when the system under test changes. And that's because the tests are too coupled to the system. Tests are often complex to develop. People complain about the cost of developing and maintaining these tests. And the history is kind of littered with bad practice and poor implementation. This presentation has a series of little things in it. So I'm going to put slides up and I'm going to stamp on what I think are the anti-patterns. So one of the little games you can play is kind of anti-pattern bingo. When the slide comes up, see if you can spot the anti-pattern before I put the stamp on it. So who owns the tests? So I think we want to have lots of these tests. We want to have, probably if it's a significant system, tens of thousands of these tests running to assert that our behavior is correct. The common pattern that I use on the teams that I work on is that we specify a story, we define the acceptance criteria for those, and part of our definition of done is that there is a minimum of one acceptance test for each acceptance criteria in the stories. That means that you build up coverage in these sorts of tests very quickly. It also means that you're probably over-testing, but it's a nice, easy way of kind of closing the feedback loop, making sure you're building the coverage without having to be too smart and too predictive about how you design your testing strategy. So it's very nice that anybody can write the tests. If you've got a technical business analysts, great if they can write the tests. If you've got a testing professional, they often have insight. But what I think is crucial is that the developers own the test through the life cycle. This is a lesson that I've spent probably in the order of about 35 years, a little bit more, doing this kind of thing. And I have never, ever seen a separate testing team owning automated tests work. This is a toxic idea. What happens is that the development teams write lots of tests. The development teams write lots of code. A separate testing team writes some tests. The developers team change the code, break the tests. The testers start trying to fix those. Meanwhile, the development team, of whom there are usually many more, carry on writing code and changing stuff, and the testing team never, ever, ever catches up. The tests spend all of their life broken and are of little value. This is a really simple problem to fix, is that you make the developers responsible for keeping the tests passing. So as soon as the developer makes a change, they notice that they've broken the test, and it's their responsibility to fix the test there and then, even if they didn't write it. And it's fine if they didn't write it. It's fine if somebody else wrote it, but they own the responsibility of fixing the tests. And I'm not a big believer in hard and fast rules, but this is very close to what I get to a hard and fast rule these days in terms of the way that I set up the teams that I work on. So developers own the acceptance test. That's kind of lesson one, if you like. It's a really important thing to get this thing working. And it's quite unusual in my experience in organizations. It's not the way that we set things up very often. So the rest of this talk, I'm going to focus on this. This is kind of my agenda for the rest of this talk, and I'm going to go through each of these things. So what are the properties of good acceptance tests? A good acceptance test focuses on the what, not the how. You focus on what it is that we're trying to assert, not how it is that we're interacting with the system under test. That's a really important distinction. This is an important separation of concerns that leads you to a certain approach to designing the tests and the infrastructure that support them. The tests need to be isolated from other tests. We want to run many of these tests. We want to run them in parallel, perhaps. We want to run them again and again. Lots of different ways we want to run them. They need to be isolated so that we have maximum flexibility. We want to be able to set the system up into a known good state and be able to assert that the things that happen to it are the things that we intend. They need to be repeatable. We want to do this again and again. We want to get the same results each time we run the test. I struggled with this one. So I've put uses the language of the problem domain. I struggled with it because the rest of these things are nice properties. This is kind of a bit prescriptive. I nearly reworded it to say they should be easy to write, but that's not strong enough. Using the language of the problem domain is a key enabling approach to making this stuff work. If you want to get the abstraction right, we want to be able to express the semantics of the test in the language of the problem domain, in the language that the business understands. It makes it more accessible for everybody, makes it easy to maintain, and crucially, it drives the abstraction, the technical abstraction that's going to allow us to implement this in a way that's going to be robust in the face of change. We want to be able to test any change. We want our build pipeline, our deployment pipeline, to accept any change and evaluate that and us to be comfortable that what we're going to see is going to work. And we want them to be efficient. As I said, we want to run thousands, probably tens of thousands of these tests in a sensible amount of time and get a result. So let's look at the first of those. Let's imagine that we have a system, and this system has a number of different channels of communication with the outside world. The details of what these are is irrelevant, but most systems of any complexity, there'll be a number of different mechanisms, technical mechanisms, through which we will interact with the system. And there's a number of groups of interested parties that, domains, subdomains that are interested in this. Let's imagine that we write a bunch of tests against such a system, okay? And let's imagine that there's a change in one area of the system which invalidates a bunch of these tests. Now, if we've done what conventionally many organizations do, and we've conflated the concerns of what it is that we're trying to test with how it is that we're going to do the testing, we're writing, the typical kind of record and playback sort of style UI test is a good example of this, where it conflates the concerns of what it is that you're trying to do with how it is that you're interacting with the system. So which buttons to push, which fields to fill in, which checkboxes to select, that kind of thing. If we've conflated those things, then the only way in which we can fix this change is to go to each individual test and fix it there. Like most problems in software development, this is fixed by introducing a level of indirection. I did go a bit animation happy in this presentation. Forgive me, it gets worse. So what we can do instead is these channels here that are represented, we can kind of make concrete. We can represent those channels as part of our test infrastructure. And the tests can interact with the system through these channels. So now, if our fix API changes and our test abstraction of the fixed API breaks all of these tests, we've only got to fix this part to fix all of these tests that are broken. So this is kind of the device driver pattern. So we're writing a device driver that abstracts how we're going to interact with our system under test from how the test cases are going to express their needs. At this level, these things are talking in business concepts. These things are placing orders, creating users, whatever it is that they're doing, creating accounts, whatever it is that they're meant to do. At this level, it's talking the protocol that the system understands, but this thing is the only thing that's responsible for kind of encoding that interaction. In this circumstance, we can fix it in the one place, it fixes all the tests. So we've kind of had a win. It's simpler now for us to maintain this. Actually, if you kind of follow this through, what tends to happen is that there's a bunch of components and stuff that kind of sits in here that forms part of our test infrastructure. So there are the concepts in the problem domain. There are the encoding of these channels of interaction that become common amongst our test cases. So we're starting to build up the idea of some test infrastructure that's specific to our problem domain and specific to the system that we're working on, but is abstract and valuable and shared amongst a variety of different test cases. Another important thing is to kind of separate the idea of deployment from testing. Traditionally, it's fairly common to think of every test should control its start conditions and should start in this application. I'll give you a clue here. So there's an anti-pattern on here. Can you guess? Yeah, it's the first one. We don't want every test to set up the application and start its own conditions, because that's inefficient. If we've got a big, complex application, we want to be running these tests in lifelike circumstances. It's going to be costly to do this for every test. So we want to separate the decision of when we deploy things from when we test things. We want to isolate the tests differently. Acceptance test deployment should be a rehearsal for production release. That's absolutely true. What we want to be doing through a process of continuous delivery is by the time we get to the point of release into production, we want to have a very high level of confidence that our release is going to work. We want to have validated that. So we want to be using the same mechanisms for deploying the system into our test environment that we will use when it's ultimately put into production, including any data migration or data provisioning or anything else, all of those things. And this is our first chance. The acceptance test stage is classically the kind of first chance of rehearsing that as we go through our deployment pipeline. This separation of concern that I'm talking about gives us a great opportunity for optimizing the process, because it gives the opportunity to parallelize the tests. We can deploy the application once and then run many tests against it. So we've just incurred that penalty once, that cost once. We can share it in different environments. If we've got this, we can kind of go at parallel and have multiple environments that we do this. It gives us many chances. And it, of course, lowers the test startup overhead. So the next thing I want to talk about is test isolation. So I would suggest that any form of testing is about evaluating something in controlled circumstances. I think that's pretty close to a decent definition of what testing is all about. If you want to evaluate something in controlled circumstances, you need to isolate it from other things. You want to limit the impact of other tests running alongside it from this thing. So there are a number of different ways in which this is true. So we want to isolate the system under test. We want to isolate test cases from one another so we can run them in parallel. And we want to isolate test cases from themselves. So if we run the test case once and then run it straight afterwards, we want it to have repeatable results. We don't want it to have left some stuff in the database that means that the second running of the test is broken. Isolation is kind of a vital part of your testing strategy. And I've seen many organizations in the past suffer when they try and create a complex network, dependency of tests. If you run this test, that sets up the start conditions for this other test, and you build this complex rat's nest, this dependency tree that you can never maintain. You break one thing in the middle and you have no idea what's going wrong. So isolation is a vital part of your testing strategy. So first, let's talk about isolating the system under test. This is kind of a typical picture in many enterprise systems. So let's imagine that you're working on system B. This is the system under test. And system B is kind of in a chain of dependencies between other systems. System A talks to it and system C is downstream. And it's fairly common in large enterprises to have an integration test environment where you kind of glue all of these things together. And it's a requirement that you're going to test in this circumstance. This is problematic. So if your mode of testing system B is to put inputs into system A, then you haven't really got control of the inputs. You can't really put the weird cases in unless you really know what's going on in system A. To be honest, if you're working in this system, you probably don't really know much about system A or C either, and so you don't really understand the inputs that you need to put in there. This kind of assumes that you have global knowledge of all of the systems, in-depth understanding, and that's just not going to happen. It ends up that this is not really in a predictable deterministic state. It means that you can't really know what state this thing is in and that whether your test is going to pass or fail. It's like trying to eat spaghetti through a letterbox with chopsticks. You're a very long way divorced from the thing that you really care about. So that's another anti-pattern. What we really want is something that's more like this. So you want a bunch, oops, sorry. Sorry. Yeah, I knew this animation was a mistake. Did you test it? So what we really want is something more like this. We want to really have control of our system. Now, we do want to be interacting with our system in realistic ways. So, we want this to be interacting through the real communications channel to our system. The API that's exposed, the user interface that's exposed, whatever it is, we want these interfaces to be real interfaces. But we want we want control. So we don't want special access for the tests, but we do want close access to our tests so that we can exercise our system as it would really be exercised. We can put wacky things in here. We can simulate the upstream system breaking and having exceptions or sending garbage downstream. We have much greater control over the state of this system, and so our ability to test it and assert against it. The trouble is that when you've got a system like this, well, the reason that people do this kind of thing is that they're worried about these bits. They're worried about the interfaces between the systems. What about the stuff that you don't expect? What about the, something changes in here that uses this, the interface itself doesn't change, but something changes in here that changes the way this interacts with this and so invalidates your tests in some way. And that's a valid concern. So I think that what we're really looking for is something more like this. We want to test those cases too. We want to test the interfaces. But actually, when you do that, the amount of testing that you need for these systems just to assert that their interfaces are good is much, much smaller than the whole thing. So now you've got much better control over the state of this system, much stronger assertions that you can make against this system, and you're defending yourself against changes in the interfaces from these systems. This is a strategy. There's a lot of devil in the detail of this strategy. This is not a slam dunk. This is not a simple solution, but in my opinion, it's a better solution. And it certainly means that you have a better opportunity for testing this thing. And there will be times where still you may get broken by changes in here that you didn't expect. But that's a better situation than trying to look after the whole world and have the scope of your testing extend forever to the bounds of the internet. So now, test isolation. So I'm going to make an assumption now that most of us are talking about multi-user systems. This isn't always the case, and if you're not talking about this, test isolation is relatively simple because then you do spin up multiple versions of the application as a way of doing that. But let's assume that we're talking about multi-user systems. Those are the systems mostly I've spent the recent years of my career working in. So what we want is that the tests should be efficient. We want to run lots of them. What we really want to do is we want to deploy once and run lots of these tests. So we must avoid any dependencies between tests, dependencies in terms of shared state, persistent state, any of those sorts of things. So what we're looking for is a way of isolating each test from the others that's going to allow us to run many of these tests in parallel against the same instance of an application. So we can start it at once, run a bunch of tests, get some results, and each test is independent. A great way of doing this is using functional isolation. So you look within your own problem domain and identify the boundaries within your problem domain that make sense and carve up your tests along those lines. So if you're testing Amazon, create a new account and a new book every time that you want to run a test. If you're testing eBay, create a new account and a new auction every time you're running a test. If you're testing GitHub, create a new account and a new repository every time you run a test. That gives you the isolation. You can set up the account or the marketplace, the auction, whatever it is, in precisely the state that's important for this given test case, and use it just for the implementation of this test case, and then it's done. You don't need it anymore. It has a weird side effect in that you tend to make the creation of accounts and marketplaces and stuff like that efficient, but it's kind of an odd side effect. The other kind of isolation that's important is temporal isolation. We want repeatable results. I want to be able to run this test, and then I want to be able to run it again, and I want to get predictable results. That's not always obvious that you can do that. So let's imagine a little bit of code here. So there's a test here I'm going to put my glasses on so I can read it out. So here, it doesn't really matter the problem domain here very much. So we're placing an order for a book. So we've got an idea of a store. We're going to create a book, which happens to be called continuous delivery. We're going to place an order for the book, and we're going to assert that the order's been placed. So the kind of the bit that we're talking about when we're talking about the isolation here is this, that this is the problem bit, if this is the book that we're dealing with. So let's imagine that what's going to happen is that we're going to execute that line, and we're going to create this book called continuous delivery. Now, the next time that we run this test, continuous delivery already exists, so the test, it's going to fail probably, or at least it's not going to be in the same state that it was the first time, because maybe we've changed the state, maybe we've changed the price of the book as part of the test. Something that may have changed. We can't guarantee that the thing's in the right state. So another alternative is the first time, so this book here is called continuous delivery in the test. But actually what we do is that we create continuous delivery 1, 2, 3, 4. So we alias the thing in the scope of the application, and the next time we run, we alias it as something else, and now we've got our isolation based on our functional entities. So it's a powerful practice to alias your functional isolation entities, so that you can have this repeatability, you can run these tests many times and get repeatable results. Each one of these is isolated because it's an actually independent case. I said repeatable lots of times. The tests need to be repeatable. So what do we mean by that? So let's imagine that we've got a system. This is our system under test, and our system under test is talking to an external system. We've already said that we'd like to try and isolate ourselves from this alternative external system. If we're good software developers and we're following the principles of design, and we didn't only learn software development for dummies or by watching any Visual Basic demonstrations in the 1980s, then we're not going to do this. We're not going to have our primary logic talking directly to an external system. We're going to have something that sits between us and the outside world to give us an option for things to change. That's good. That's nice. That's a slightly better design. It's a better separation of concerns. I would say that this thing is focused on presenting a nice interface, whatever your definition of nice is, to your model here of this outside world thing. The next level is that there's kind of, there's the actual communications that's going on with the outside world. I would suggest that's a separate concern from this, because this is focused on giving some nice interface here. This is just the communication channel to this thing. So if you have that kind of architecture with this little plug-in here, you have the opportunity to have an alternative plug-in. So you want to test this interface, because this interface is doing useful work. It's mapping between your concepts and the outside world's concept. This thing is just wire protocol stuff. That's just boring. That's easy to do. So you can separate these concerns, and you can kind of define this through configuration, and then you can have something different in your external system to your production system. In this instance, we've got a stub of our external system, so we're faking this interaction with our external system. The real communication channel is still being exercised here. The real thing is, it's still talking as though it would in the real world. It's just not really talking to the external system. So this is really about where that sits in terms of the test infrastructure. So we've got our interface, here's our system under test, here's our external stub, test infrastructure, and there's a bunch of test cases. What I'm talking about is this thing being enrolled as part of the test infrastructure. There is some back channel of communication to this stub here, so I can collect results from my test interactions and submit inputs through this via my test infrastructure, whatever that means. This means that I have, within this test infrastructure, abstracted, so my test cases can talk to the thing. I can express these things. I can say what I want of the external system, so I can simulate different behaviors and so on through the real communication channel into my external system. Uses the language of the problem domain. So I've kind of been leading you gently in the direction of talking about domain-specific languages. So what I'm talking about here is abstracting. A DSL allows us to solve many of these problems. If we start approaching this and encoding our test cases in a domain-specific language and developing our domain-specific language, it gives us the right level of abstraction. It gives us readability. It makes it easy to create the test cases, easy to maintain the test cases. It gives us a natural separation of the what from the how, and it gives us the ability to do the test isolation as I've just described in a variety of ways in this infrastructure that I've been drawing pictures of. So here's a simple example of such a DSL. This is a real one. This is from projects that I worked on. There's a couple of examples here. And you can see that, this is a thing called an internal DSL. So this is a DSL that is actually executing, in this case, in the Java language. So it's written on top of Java. We execute these things using JUnit, but they're complex acceptance tests interacting with the system. And it's kind of a very stylistic form of Java, which is the DSL bit. I think it's fair to say that you can imagine somebody that's not a programmer, that's familiar with this, understanding what these test cases are. These are about as clear as a templated Word document or Excel spreadsheet defining manual test cases. This is what I mean about the idea of executable specification. There are organizations that use some things like these as the support documentation for the system. So make a support call, you call up the support person and say, this is going wrong, and they can search through the tests and say, well, the test says it behaves like this. And they will know that that's the case because that is the test that's run against that version of the software, and so it's a very strong assertion. It's not a weak link between a document that may have drifted, may be different to the version that's in production. It's the test that was run against that version of the software in production. This is a very strong link in terms of specifying what it is that we want of the system and getting the results out. But I think you can imagine it's relatively easy to write this without knowing how the system works in detail from a technical level or how the test interacts with it. The bit that I'll ask is, here's the typical setup that's kind of creating, and we called them instruments in this case, so that was a market that you could trade in. It's creating a user and so on. So it's doing the aliasing stuff that I was talking about earlier in order to isolate this test from any other tests and from running it multiple times itself. Underneath the covers, in the implementation of the DSL in this case, there's quite a lot going on. So we can specify simple things at a high level, just the stuff that we care about, but there's also a lot of default parameters in here. It's actually a very powerful thing. We can go into a great deal of detail to specify precisely the state that we want the system to be in when it's under test. Or we can just take the defaults and write stuff very quickly and move on. This is kind of nice. It's arm's length. It's abstract. There's still a little bit more coupling than needs to be. And actually later in the life of this system, it kind of evolved a bit differently. So you can see here, we're talking about the trading UI and the deal ticket and the fix API. So this was a trading system. So you could either go through the user interface, which is the trading UI here, or you could go through the fix API. If you're not familiar with fix, it doesn't matter. It's just an application programming interface that's common in the finance industry. And that's okay, but it's kind of coupling the channels a bit. So later we kind of evolved to this. And this was even nicer. So now we've got an annotation which defines the channel that you could talk through. So we could, the fix API, the deal ticket, the public API, and this test could be executed against all of them. So we're getting to the stage where it's quite easy to write these tests very quickly. This is very, very loosely coupled with the system. You can imagine very significant, dramatic changes. In this case, the difference between a rich web user interface and a fix API or a binary API, which is the other one that's listed here. And it doesn't matter to the test. So this is very loosely coupled, but very fully specified in terms of our ability to control the environment and set the system under test up into the state that we desire it to be in. And you can kind of, encode stuff like the domain. You build your domain over time to evolve your domain, your domain DSL, your domain-specific language, over time to match the testing as it grows, as you grow the system itself. This is an evolutionary approach. We want to be able to test any change. So test cases need to be deterministic. Time's a particular kind of problem when it comes to determinism, which is often ignored. I think that broadly there are two approaches. You can either ignore time, so you can every time your system talks about time, you just ignore that value and pretend it's not there and you don't bother validating it, or you can deal with it. So ignoring time, you can filter out time-based values in your test. It's nice and simple and it works for some cases. Often though, that's not enough. Certainly if you're talking about a complex enterprise system, you probably can't ignore time. There are probably useful test cases that you're interested in being able to evaluate that involve time. So the alternative is to control time. So my approach is treat time as though it's an external dependency like any other. It's an external system. Treat the supply of time information as you would any external system. And stub it, control it, strategize it so that you can change it. This is very flexible. It's a very nice way of doing it. It allows you to simulate time-based scenarios. You can have long-running scenarios in your test that execute very quickly. So in the exchange where some of these examples come from, we could run daylight savings examples. We could test daylight savings changes through our system by fast-forwarding time so that it crossed over a daylight savings boundary. We could run clearing examples where, so classically in finance, you clear 3 days later, so you could kind of rewind the clock forward 3 days later and test all of those scenarios. So it gives you a lot more control. It's slightly more complex in terms of the infrastructure. So here's an example of such a test. So you can see I'm selling my book. So let's imagine you're borrowing a book and the book's not overdue. You've only just borrowed it. So time travel 1 week, the book's still not overdue. Time travel 4 weeks, the book's now overdue. Okay, it's a simple test, easy to understand, and it's quite a nice way of expressing it. Sorry, that you're quite right. That should say assert true. This is the first time I presented that. Thank you for being my system test. Sorry? Did you see that fail before you saw it pass? No, I confess this one's a PowerPoint-only test case. The others were real. So what am I talking about? So again, here's my pretty picture of a system under test. And here's some behavior of the system that's time dependent. Classically, this is the kind of thing that we'll do. We'll make a system call to get the current time. So another way that we could do it, again, we're using one level of indirection. So let's introduce the idea of a clock. So we'll have a clock that sits between us and the system time. So it's doing the same thing under the covers. It's going to do the system. But now our system under test only ever accesses time through this mechanism. So here's an example of a clock. We've got a clock which by default is a system clock, which is just going to do what it was doing before, look up the system time. But it also allows us to change that. It's public. You could probably not write the code neater than that. You could put accessors or whatever from your technology. I was just trying to keep it simple. Sorry? It does, yeah. But still, I want to be able to change that and not change the real time, real underlying time of the system and all that kind of thing. So here, again, part of our test infrastructure under control of our DSL, as I demonstrated in the previous example, we've got some stuff. So here we're going to, on initialization, we're going to change the clock. So instead of using the system clock, we're going to override that and we're going to use the test clock. And now, when we call time travel, we're going to have a new time. We're going to parse that time from a nice string representation that's pretty in our DSL, and we're going to change the time in our clock. Now we've got control of time, and our DSL can do the fast forward thing, move time on, and test all of these complex scenarios. The other thing that's kind of interesting is tests that need a special environment. So I talked a lot about sharing environments and being able to run lots of these things in parallel so they don't crunch into each other. There are some kind of tests that's hard to do. If you're doing what I've just described, if you're time traveling, you don't really want to running tests that aren't time traveling against a system where you're time traveling, because that's going to confuse things. So you probably want to separate those things. A good way of doing this is you tag the tests with whatever the difference is, and then you use an allocation strategy at the point at which you're deciding to run the tests to deploy those to environments of your choice. So, for example, a time travel test could be treated in a certain way. A destructive test where you're killing bits of the system to see how the system works under failure, or a test that depends on specific hardware or something like that, could all be tagged, and the thing that allocates your tests out to your test infrastructure can use those tags and determine where to put them. Here is a nice visualization from an ex-colleague of mine, Mark Price, of precisely that in play. So in this case, we've got a series of parallel tests, so that's kind of the norm. That's what I was talking about. You have one infrastructure running a whole bunch of tests in parallel. And here we have a bunch of time travel tests where each one of these nodes will start up a new instance of the application, and that will be owned within the scope of the test, so we can time travel it under the control of the test. And then we have some sequential tests. Mostly these were destructive tests where we would be killing different bits of the system to see that the system was robust in the face of change. Which also you couldn't do while you were doing other things. It's kind of a trivial visualization, but it kind of shows the dynamism that's possible with these simple strategies. So the last of my properties of a good acceptance test is that they need to be efficient. We want to have thousands or tens of thousands of these things. We want the ability to be able to evolve our test coverage as we're adding new requirements and new stories to our process. We want to add a new test case for each acceptance criteria of those stories. So we're going to end up with a lot of these things. So if your production environment looks like this, when I say running these tests in a production-like environment, this is probably asking a bit too much. If you're Amazon or Google, you don't have two lots of hardware infrastructure, Amazon or Google size, in order to do this kind of thing. So what matters? So a typical interaction looks like this. Then clearly the selection of your hardware for your test infrastructure is going to look something like this. If it looks like this, and then the selection of your hardware is going to look like this. What we want to do is that we want to be representative of the key concepts. If you've got a distribution boundary that's important in your system, it's probably important to represent that. Depending on the nature of your system, it might be important that that's using the right kind of network card. I'm from low latency finance. That shit mattered in my world. Maybe it doesn't, but you could simulate that with a VM. It doesn't matter. But you need to represent the stuff that's important in your deployed environment. If the hardware is different in this machine to this machine, you need to represent that if that's significant to your application. You want to be testing in scenarios that are lifelike, because that's the stuff that will catch you if you don't. The other thing that's important about efficiency is to make sure that each test is running efficiently, so that you don't want to be wasting, you don't want to be spending inordinate amount of time in each test. I would suggest, so the kind of mental model that I have of an ideal cycle time is, the kind of mental experiment is, I imagine a disastrous situation going on in production. You know, something really bad's happening and we're losing money. Okay, in production, you know, or users or whatever it is, something bad's happening. I want to be able to still go through my deployment pipeline at this point. I don't want to be bypassed. This is the time where I want to be sure that my change is safe. I don't want to be making the situation worse. So I want my cycle time to be short enough that I can get a result and get that emergency fix out in a timely manner, but still be confident that the change is good. So I don't want to be spending days running these tests. Ideally, I don't want to be spending hours. So generally, my rule of thumb is that I think that a reasonable compromise between having enough time to run a reasonably complex, involved test is somewhere in the order of about 40 minutes or something like that, maybe an hour for these things. That's kind of my rule of thumb. I tend to try and operate at that kind of level for these sorts of tests. One of the things that tends to trip you up with this, in terms of inefficiency, that's very common, is putting wait statements in your tests, particularly when you're dealing with asynchrony. I would suggest it's a really important point when you're dealing with asynchronous systems, and if you're not, you probably should be looking at doing that because they're much more efficient and easy and have fewer problems. But one of the things is to look for a concluding event. So you place an order and there's some other event that happens later after that's successful, and catch that. So you don't want to make your system synchronous just to make your tests work, because asynchronous systems are faster and more efficient and easier to reason about. But you do want your test cases to be synchronous, because you want it to do a step and then move on. At the level of the DSL, each line in your DSL is synchronous. You don't want this to be a complex coding exercise. You want anybody to be able to understand the sequence of events and the flow through your test cases. So here's a trivial example. Imagine that this is the implementation of a place order method within the DSL. So this is the thing that test cases will call. And what you want to do is you want to separate the concern. So you're going to send an asynchronous place order message, which is parsed from the params that were passed in. And we're going to wait for an order that the order was confirmed or fail on a timeout as a separate step. That way, we're presenting it in the test case as though it's a synchronous call, even though it's not. Just as an aside, it's kind of useful in the DSL as one of those little green blobs that I showed earlier in my diagram to kind of have the key domain concepts. In this idea, the idea of the order is a useful concept. So there's probably some stuff that you'd like to remember about that, and it's probably material to a bunch of different interfaces of, as part of the implementation of the DSL that you kind of roll up into this in terms of your implementation. So if you really, really, really have to do a poll and timeout mechanism in your do it in your test infrastructure, not in your test cases. But this first way, looking for the concluding event, is a much stronger strategy. And please don't put weights and expect your tests to be reliable or efficient. They will be neither if you do this. If you've done all of this, if you've taken this approach, then it makes this next bit easier. So what tends to happen over the life of a project is you start off with a relatively simple test infrastructure, and then your 40 minutes duration starts getting eaten into it in no time at all. It's taking an hour and a half or 2 hours, and that's not good enough. So you want to throw some hardware at it. You want to parallelize it. So let's imagine we have something in our artifact repository. We've got some coordinating function that's running our acceptance tests. We're going to deploy that release candidate to our acceptance test environment. Then we're going to spin out a bunch of parallel test hosts that are going to run all of these tests in parallel against this thing. This is kind of nicely, widely scalable to kind of the limit of performance of your system. So you can kind of turn up the dial. You know, if you want your test results in half an hour, buy some more hardware, buy some more VMs, go to Amazon and buy some of their services. You can scale this stuff up. When I left LMAX, which is a while ago now, we had something like, I think it was about 25,000 of these sorts of acceptance tests covering all aspects of the system. We got a result in about 40 minutes. If you ran them serial, if you ran them end to end, it took over 30 hours. So it's an effective strategy, this parallelizing things. So I'm going to wind up with some quick anti-patterns, and forgive me, I'm going to put my glasses on because it's easier to read here than up there. So don't use UI record and playback systems. They're too brittle, they're too tightly coupled to the system under test, and it doesn't work. Don't record and playback production data. This has a role, but it's not acceptance testing. You want to control the state of the system under test. If you're just recording back production data, if that's your only approach to testing, you're only testing the common scenarios that happen to have occurred in the recording of that set of test data. You're not getting the weird outlying circumstances. You're not testing the exception cases, and mostly it's the exception cases that you want to simulate because those are the ones that are usually going to kill you. Don't dump production data in your test system because you want it scalable, you want it to be nimble, you want to be able to deploy this out all over the place, you want to have flexibility to be able to scale this up very far. And if you've got vast amounts of data, you're not going to be able to do that. Don't assume some nasty automated testing product, trademark, is going to do what you need. Design your test strategy. You decide what it is that you want out of your test strategy and evaluate things in that context. Don't have separate QA team. Having human beings who are specialists in testing is a very good thing for many teams. I'm not saying don't have QA people, but don't have them writing the acceptance tests as separate to the developers. Developers own the acceptance tests. Let every test start. Don't do that either. Don't include systems out of control. Don't put waiting instructions. I've talked about all of these. So do ensure that your developers own the test. Can you tell that I care about that? I've said that quite a lot now. Do focus your tests on the what, not how. Do think of your tests as executable specifications. Do make acceptance testing part of your definition of done. Do keep the tests isolated from one another. Do keep your tests repeatable. Do use the language of the problem domain. I recommend that you try this DSL idea. This is not language specific. It doesn't have to be Java. I've done it in Python, Ruby, Java, fitness, all sorts of different ways. It's the idea that's important. It's the separation of concerns that's important in this pattern, not anything else. Sorry, pattern is probably a bit strong use, but do stub external systems. Limit the scope of your testing to the thing that you care about. Test in production-like environments because that will catch things that you don't expect. Do make instructions appear as synchronous at the level of the test case, and do test for any change. We want to be able to have a very high degree of confidence that at the point at which we push the button, we're probably likely to be okay. We can never write enough tests to prove that our software is good, but we can write enough tests that if one fails, it tells us that it's not good. Falsifiability is an important part of this whole strategy. And do keep your tests efficient. We want to have lots of them. We want to be able to make them easy to write, easy to maintain, and cheap to run. And with that, I'm done. So,
questions? We have plenty of questions.
Cool.
Do you unit test your acceptance test abstractions in DSL?
Yes, sometimes. So some of the more complex bits, so some of the infrastructure, yes. There is the stuff, the examples that I was using from LMAX, there is an open source version of the kind of test infrastructure. It's a really, really simple project. It doesn't do very much. You have to do quite a lot of stuff to build your DSL on top of it, but it does some of the aliasing for you, gives you the defaulting for properties, that kind of thing. It's called Simple DSL, and it's on the LMAX open source website. That's worth a look. But some of that's unit tested, some is not. We tended not to unit test as we evolved the DSL, but we did tend to unit test the infrastructure.
So judging by the examples where you see, you seem to be advocating for using multi-kernel DSL or very certain ones such as Cucumber. So what's your...
I'm not strongly against Cucumber or the other things in that class. My personal experience is in the use of internal DSLs. I think they have the nice properties that if you want the developers to own the tests, then you're in the tool set of the developers. You're in their world. You're using the languages that they're familiar with. It makes it easier. You do want to be able to run you do want the developers to be able to run any of these tests in their local development environment. And so I think that's a win. So I'm not anti-Cucumber or anything. I am anti a separate QA test team writing Cucumber tests, as I think I've made the point.
Do you write tests fail in with?
Yes. Yes. So generally, I would advocate writing the test first. It's a nice way of focusing your mind about what it is that you care about the story. If you do treat these as executable specifications, it's nice to treat these as your definition of done. You know, so once the test passes, once it passes once all of those tests pass, you're done. What else is there to do?
Yeah, I'd like to question slightly the anti-pattern about starting the app for every test. It seems there's a couple of assumptions baked in there. One is that that is necessarily slow. I don't know that it necessarily is. Another thing is that by doing that, you break isolation, but you introduce the risk that the first test can change something internally in memory that then blows up in test 89. And that can be a massive maintenance burden. And in the light of what you said later about parallelizing, I would question whether that was always the right trade-off to make.
I would agree that it's not always the right thing to do. However, in the sorts of systems that I work on, it's always been the right thing to do.
And maybe you need to say more about what those systems are.
Sure. So I'm on the whole talking about large-scale enterprise systems, big complex systems. Essentially, it's down to can you start it up in under a second? If you can't start it up in under a second, it's probably too expensive to do it for every test case.
And what's your parallel environment like? Because,
big and complex.
Yeah, well, if you've got a lot of parallel stuff available, then a 5-second startup might be all right, or a 10-second startup, if everything's going at once anyway, against the previous.
Maybe, and that's a calculation you have to do.
Yeah,
but
I think it's a bit simplistic to just call it an anti-pattern and write a red cross over it.
Maybe. So in the systems that I'm talking about, you know, it's certainly an anti-pattern. Really, what I'm talking about is making sure that you've got control of the environment.
But he's doing exactly that and being very successful with it. So labelling it an anti-pattern is a bit blanket and sweeping.
Sure. Okay.
A pattern by definition is sweeping.
Yeah.
We're saying we have a counterexample.
Yeah.
Yeah.
No, hey, there are always counterexamples to a pattern. I'm sure there are people out there that say do food doesn't work to Linda.
Quick question about when you were testing against test stocks, do you use the same artifacts that you would put into production, but just switch out the components?
Yeah. So generally, with hindsight, I'm not quite sure my picture shows it, but the idea is that what you're talking about is that the plug-in bit is kind of the external bit. So you are communicating with the application through its natural interfaces. So you're not changing anything that's kind of the runtime property of the thing. This thing is really simulating the external bit, not the internal communications. Does that answer your question?
There seems to be, like the other question said, an inherent tension between isolation of tests and performance.
Yeah.
And I've encountered not resetting the database enough, causing significant delays. Do you have any insight into how often should you reset
That's where I think the functional isolation thing comes in. So I don't like the idea of resetting the database in the life of the test. If I'm going to do that, I want to blow it away and redeploy the application and do whatever it does from a known good starting position, including any data migration or anything, because I want to rehearse the deployment. So I don't want the state to be in an artificial state that's under control of the test. I don't want to be going under the covers of the system in order to set the state up. I want to be going through real external interfaces of the system to get the system into the state that I want it to be in.
So, are you saying reset the database in between every test?
Yeah. Sorry, no. In between every deployment in the test environment. So if it's a complex system, I'm going to start off from maybe there's some reference data in my test data sample, I don't know, but I'm going to start off with the same position every time, and I'm going to use the deployment tools that I will use in production to migrate that to the new version of the schema or whatever to get it into the state, and I'm going to use my DSL to get the system into the state that I want it to be in order to be ready for the test. Yes, it is, and that's what the functional isolation is about, to try and prevent the need for you to reset the data. So I'm going to isolate the scope of my test, within the functional entities that make sense in my problem domain, and that should give me the isolation that I need.
Any tips on convincing a dedicated acceptance testing team that they're anti-pattern?
So are they keeping up with the development team? Are their tests broken all the time? Fix that problem. So if they are, then I'm wrong in that circumstance, and fine, whatever works ultimately. But my experience is that I've never seen that work. They're always lagging. The tests are always breaking. And so the way to close that loop is that they're still important. They still add value. They can be delivering the vast majority. They can be creating the vast majority of the tests. But as soon as those stories are released, or the developers have implemented the behavior that fulfills those tests, the development team own them. And they have responsibility for fixing any breakages. That's the point I'm trying to make.
And the developers are always behind the bugs that are raised as well.
Yeah.
One more, please.
Any tips on getting a development team that's used to having a dedicated acceptance testing?
No. It's one of those cultural things. You need to win people over and get them. The one thing that I would say, that the teams that I've worked with that worked like this wouldn't go back. So the teams that I've worked with regularly grumble about how difficult and onerous it is to stay on top of these tests, keep all the things working. It's hard work, it's difficult, but the safety net that it provides is so valuable that they wouldn't go back to doing it any other way. Thank you.